Hey folks, welcome back to another lecture in the Introduction to Earth Sciences lecture series. I'm Dr. Matthew Wielicki. Please follow me at Matthew Wielicki on Twitter, subscribe to this YouTube channel, as well as check out my Substack, noclimateemergency.substack.com. We're going to keep talking about rocks. So last lecture we talked about one of our three main types of rocks in what we call the rock cycle. We talked about igneous rocks. And those rocks were formed from molten magma or lava. They're rocks that essentially crystallize from a liquid, and the crystals will grow. That depends on whether they grow at the surface or within the crust, and that kind of dictates what our igneous rocks look like. You're likely familiar with igneous rocks if you have a granite countertop. Granite is an intrusive igneous rock. Today we're going to talk about a little bit more what's happening near the surface of the Earth, because at the surface we have weathering, and that weathering helps to promote things like erosion and transportation and deposition of sediment, little fragments of other rocks. And eventually those little fragments of other rocks can be lithified or essentially glued together to make the second of our three rock types that we'll talk about, which is sedimentary rocks. And sedimentary rocks are very important in terms of telling us about the history of our planet, because it's sedimentary rocks that maintain things like environmental clues and data, as well as our fossil record. So let's talk a little bit more about sedimentary rocks. Before we do, I want to remind folks about a couple key principles that geologists or earth scientists use in order to be able to do geology. The first one is uniformitarianism. And this is essentially the principle that the physical processes that we observe today are responsible for forming of ancient geologic features. To put it more concisely, you can think of it as the present is the key to the past. For example, if today we observe how ripple marks form, and they form in usually with liquid interaction with sediment. If they're symmetrical, that water is usually moving back and forth, for example, near wave action. If you've ever been down to a beach and you've seen the waves lapping up onto the shore, you may have noticed that sometimes the sand has these unique ripple marks. And if we look at an ancient geologic formation like you see on the right, that's 150 million year sandstone in Colorado that has clear depictions of ripple marks, we can assume relatively safely that the same type of environment that we see ripple marks forming today was responsible for forming those ripple marks in the past. And as we use other clues, we see that that's likely true, that about 150 million years ago, there were these shallow inland seas that went through the center of North America, the interior seaway, and there was likely beaches in places that are modern day Colorado that clearly don't have water, don't have a coastline in the present day. So uniformitarianism is essentially how we do any sort of earth science, and this is an assumption that has to hold true because we don't have a time machine, we can't go back in time, but we think it's a safe assumption to think that the laws of nature and the physics that drives a lot of these processes was the same a billion years ago, 4 billion years ago, than it is today. Another key concept is the idea of superposition. The idea of superposition is the principle that the youngest layers are deposited on top of older layers. So in an image like that you're looking at, the older material will be at the bottom, the younger material will be at the top. We just don't really know of a good mechanism where nature could essentially open up this pile of sediments like a deck of playing cards and slide a new card in between, a new layer of sediment. There's just no physical process that we can identify that could do that. So usually in an undeformed sequence like this, it's relatively safe to assume that the older stuff is at the bottom, the younger stuff is at the top. Now this could be flipped over, but usually for natural processes to flip a big package of sediment like this over, you're going to see deformation in the package, so there should be some clues. So that wouldn't be an undisturbed sequence of rocks, but in an undisturbed sequence of rock, it's a relatively safe assumption that the oldest stuff is at the bottom, the younger stuff is at the top. This is the principle of superposition. We use this applications of things like uniformitarianism to study other planets. Mainly, or some of our major evidence for running water on the surface of Mars is the fact that the geologic formations that we identify on Mars look very similar to geologic formations that we find on Earth that we know are created through the interaction of water and rock. For example, this is a rock type known as a conglomerate, where you see these kind of rounded pebbles. These rounded pebbles are usually indicative of stream flow. Rocks usually don't break in these nice rounded patterns. They're usually very irregular, but as a pebble rolls down a stream and is carried downhill by gravity in the presence of water, it's bouncing around and it's knocking the little sharp edges off, and it starts to round the rock. And so where we find these deposits on Earth, like you see on the right, they're almost always indicative of running water. And although we don't have running water on Mars today, we find many of the same types of deposits that lead us to believe that there was running water on Mars in the past. And this is essentially an application of planetary uniformitarianism. Also, we find, for example, deltas. So on Earth, we know that deltas are the intersection between a relatively stagnant body of water and a stream of water, and that stream is confined to the channel. The velocity is usually relatively high, but as that stream enters a larger body of water, it slows down, and as it slows down, it drops a lot of the sediment that it's carrying, and it creates what we call a river delta. We also see evidence of river deltas on Mars. And again, this is essentially the application of planetary uniformitarianism to suggest that Mars had running water in its past. Sedimentary rocks are very important. Although they don't make up a large fraction of the rocks of the crust, and they're not really present in the mantle at all. The mantle is about 100% igneous rock, and the crust is about 95% igneous rock. Sedimentary rocks are still very, very important. It's the sedimentary rocks that are essentially the pages of Earth's past. This is an image of the Grand Canyon, the beautiful layers that are exposed as the Colorado River has been cutting down into the Colorado Plateau. And what we see is that it's these sedimentary rocks that really tell us a lot about past environments, about the plants and animals that were there, about where the rivers were, where the lakes were, where the coastlines were. When we melt these rocks to make, for example, an igneous rock, we lose a lot of that information. And you'll see when we speak about our last rock type, metamorphic rocks, that those rocks undergo so much heat and pressure that we lose a lot of the information of past life and past environments in metamorphic rocks as well. So it's really the sedimentary rocks that are the pages of Earth's history. Let's define a sedimentary rock. A sedimentary rock is a rock that forms either by the cementing, so that's another way of saying gluing, of fragments of pre-existing rock, or the precipitation of mineral crystals out of a water solution. So here in this image, we have sand on the left. That's a sediment. We can take that sand and essentially cement it together such that we make an aggregate of minerals, because that's our definition of a rock. And then we end up with a sandstone. We no longer have loose sediment. We have a sedimentary rock that we call sandstone. I'll show you that there's some other examples of things like, for example, salts. If you've ever left a pot of boiling water on the stove and allowed it to fully boil off, you may have found a white residue around the pot. That is a sedimentary rock that you made, because the water will leave into the vapor phase, but it will leave behind some of the minerals and salts that are dissolved in the water. And that's another way that we can make a sedimentary rock, is through the precipitation of minerals from water solutions. We classify sedimentary rocks really based on their mode of origin. We're going to focus mainly on clastic sedimentary rocks, which are little bits of other fragments of rocks that are glued together to make another rock type, sedimentary rock. But we'll also touch a little bit on biochemical, organic, and chemical. So this is our definition of a clastic sedimentary rock. This is a bunch of sediment that has been lithified. Lithified is just another term for made into a rock. So Lithify, litho is rock. Lithify means to make into a rock. Sometimes you'll hear us talk about lithofaction. That's the actual process of cementing and gluing these little fragments together to make another rock. And so this is our example that we just showed a minute ago. Take sand, glue it together or cement it together. Another way to say is lithify it together, and you end up with a sandstone. Biochemical sedimentary rocks are formed from material that came from living organisms. So this would be, for example, bones, shells, teeth. The image here you see is a rock type we call coquina. Coquina is essentially fragments of shells that have been lithified together to make a rock made out of shells. Shells are created by organisms that live in the marine environment to help protect them from predation. And as they break apart, they make little tiny fragments, and then there's some that are actually whole. And if this material gets buried and glued together or lithified together, it makes a sedimentary rock. But this isn't really fragments of pre-existing rocks. This is biochemical fragments because these were made by living organisms. Coquina is our best example. We also have organic sedimentary rocks. We're going to spend a whole chapter talking about these when we start talking about energy resources. Our most common example of an organic sedimentary rock is coal. So coal is essentially the buried and lithified remnants of ancient plants, usually, for example, swamps. And as that material gets buried and we increase the heat and the pressure, we take all that loose material that maybe you've seen before in the form of peat. If you do some gardening, people will put peat out into their garden. That's a very organic, rich type of essentially soil, but it's relatively loose material, and you can compact it and lithify it into the type of coal, for example, that we mine here in Alabama, which is subbituminous coal and bituminous coal. But we'll spend a whole chapter talking about this when we talk about energy resources. A third type of sedimentary rock we touched on already a little bit. This would be known as a chemical sedimentary rock. So this is the precipitation directly from solution. If you've ever gone into a cave, you may have seen stalagmites and stalactites. A good way, those are both speleothems. Those are essentially the hanging kind of pillars that we'll see, or sometimes coming out of the ground, that we see in caves. These are limestone precipitates. This is water that is leaking into the cave as it's percolating down or possibly seeping out of the ground. It is picking up lots of minerals, and those minerals will be left behind as the little water droplets will evaporate. And so over long periods of time, what you end up getting is you get these little hanging pillars that come off the ceiling, which we call stalactites. And then you also get sometimes pillars that start to come out of the ground as water seeps into the cave from the ground, which we call stalagmites. A good way to remember that is the ones that are growing out of the ground are fighting gravity, so they have to be very mighty. So they're the stalagmites as they grow out of the ground. The stalactites are those that are hanging off the ceiling, like you can see in the image in front of you. But this is a chemical sedimentary rock. Essentially, table salt is another example. So if you've ever seen an evaporation pond where near a place that is producing salt, they trap a lot of salt water. They fill in these shallow ponds, and then they block them off so that they evaporate. They don't have an inlet. The water will go into the vapor phase as it evaporates, but it will leave the salt behind, and we will precipitate the mineral halite, which is a chemical sedimentary rock. Let's focus on clastic sedimentary rocks. Those are the most common type that we see, and that's what we focus on a lot in this lecture. So clastic sedimentary rocks, just a reminder, are the rocks that are made out of little bits of pieces of other rocks, and they essentially take 4 steps to be created. We need to create the precursor of the sedimentary rock, which is the sediment, so we do that through weathering. We need to remove that sediment and transport it somewhere where we can start to bury it. We call that erosion and transportation. Eventually, we need to deposit the sediment such that we can lay it down and eventually bury it, because you'll see that it takes heat and pressure in order to lithify the rocks, which is the last step, lithofaction. This includes burial, compaction, and cementation. Let's look at these individually. The first process that is required is weathering. This is the process that breaks up and solid rock and eventually transforms it into sediment. And this is going to come in some different flavors. The two essential modes of weathering are physical, or another term for that would be mechanical weathering, and chemical weathering. So the physical weathering is actually the physical interaction of a rock, of something acting on a rock. Me going into the field with my sledgehammer and whacking on an outcrop so that I can bring it back to my lab is a physical weathering process. For example, the image we just saw a moment ago with a big tree root growing into a rock, that's a physical process. It's physically breaking the rock apart. As opposed to, for example, chemical weathering. This is a process where it's the chemical reactions, usually in the presence of water and air, that is driving the breakdown of the rock. And both physical and chemical weathering can break down rocks at the same time. These processes are working in unison. There is chemical reactions going on at the surface, but there also may be a tree root growing into a crack. Physical weathering some examples of physical weathering are, for example, frost or root or salt wedging. I'll show you a couple pictures of that. Release of pressure, which we call unloading, thermal expansion, and biological activity. So here's an example of frost wedging. You can imagine that in certain elevations, we have a freeze-thaw cycle that happens regularly. For example, even here in the southeast in the wintertime, there's a lot of nights that will go below 32 degrees Fahrenheit, but then it will be in the 50s in the day. And what that means is that little cracks that exist in the rock will fill with water, whether that's dew from the night before or just precipitation or groundwater infiltration. There'll be, in the southeast where I am here in Alabama, it's pretty wet. We have quite a bit of rainfall essentially every month. We have on the order of about 4 to 5 inches of rain every month. And so these cracks will fill with water, and because water has this unique property that it expands when it turns into the solid form ice, it starts to work and actually wedge the rock apart. We call this frost wedging. And although it's doing it at a very small scale, the expansion of water is very small, over thousands or millions of years in geologic time, this can have a significant impact on expanding cracks in the rock. As certain rocks are exposed at the surface, for example, if you've ever had the great chance of going to see Yosemite Valley, I grew up in Fresno, California, which is only about 45 minutes from the gates of Yosemite. Yosemite has these really unique rock features. The granites of Yosemite appear to be peeling like an onion. You can see the image on your left, where you can see these distinct layers that are kind of fracturing off and sliding down the hill. That's because the granites that exist in Yosemite Valley, they crystallized deep within the earth. Long before the Sierra Nevada mountain range was exposed, there was volcanic activity where the modern day Sierra Nevadas are. In fact, at the very northern tip of the Sierra Nevadas, we still have active volcanism in the form of Mount Lassen and Mount Shasta. As the Sierra Nevadas were uplifted and exposed at the surface, what happened was there was a lot of material above that was eroded away. And so when we erode that material away, we remove that overburden pressure. And what happens is the rocks start to expand a little bit. And as they expand, they start to break off in almost these sheet-like layers. Almost looks like you're peeling an onion. If you ever go hiking around Half Dome, for example, in Yosemite, you'll see these very distinct features. We call this unloading or pressure release. This is, again, a physical characteristic that is breaking the rocks apart. We're not invoking any sort of chemistry. This is just physical unloading of pressure. Chemical weathering is a little bit different. Now, we're not going to have a physical or mechanical action on the rocks. We're going to have a chemical reaction, usually in the presence of water or air. And the three most common are dissolution, hydrolysis, and oxidation. Let's look at those individually. Dissolution is the dissociation of a mineral into its constituent ions. So this is essentially dissolving. Take salt, put it into water, and it dissolves. It dissolves because, remember, it's ionically bonded. We talked about this bonding structure when we talked about minerals in the first place. So table salt, or the mineral name is halite. It has an ionic bond. The sodium atom loves to donate an electron, so it becomes positively charged. The chlorine atom loves to gain an electron, and it becomes negatively charged. Opposites attract, and we have an ionic bond. That ionic bond is relatively weak, though, because we know that just putting a little bit of salt in some water and stirring it around is sufficient to break that bond. Oxidation. This is the chemical reaction of a mineral with molecular oxygen. This is essentially rusting. If you've ever had an older vehicle and maybe had a paint scratch on it, the body of most vehicles is made out of steel. Steel has a very high component of iron. That iron, that paint scratch, allows oxygen in the air to start to interact with the underlying steel because the paint has been removed where the scratch exists, and you may see some rusting, some reddish color. This is essentially the transition of iron from FeO to Fe2O3. It's oxidation. It's adding oxygen to the iron structure, and it weakens it. I used to have a very old Jeep back in the day that had some big rust spots where you could almost push through the floorboards because the original steel had become so weak due to rusting. But the same thing is happening in rocks that contain a high component of iron. If they're exposed to oxygen, as most rocks are at the surface because our atmosphere is 20% oxygen, they start to react with that oxygen, and it weakens their chemical lattice or their crystal lattice in their structure. Hydrolysis is when water reacts with minerals to form a new mineral. And this happens routinely in the formation, for example, of clays. Clays tend to be hydrated bits of other minerals that were transformed by the reactions with water. All of these are chemical reactions, but they're all working to do the same thing that physical weathering was doing. They're all working on breaking the rock apart. And it all really comes back to the factors that are affecting weathering being how much of the rock is exposed, how strong is the rock, what is the rock's composition, and what type of climate does that rock exist in. Right? So the more surface area exists, the more of these chemical reactions can be going on, the more cracks there are for roots to get into or water to get into to wedge the rock apart. The composition of the rock is really going to tell us how strong the rock is. So the rates of weathering can be very fast in one environment because the rock type is relatively weak, and relatively slow for other rock types in that same environment because the rock type is relatively strong. And also the climate, because a lot of the chemical weathering requires the interaction with water and air. That means that areas that are relatively warm and moist will have a faster rates of weathering than areas, for example, like deserts that are relatively dry. The surface area is likely the most important factor in the rates of weathering. And the surface area is a positive feedback loop with weathering, both chemical and physical. So here's an example of a single cube of rock that we start to divvy up into 8 cubes and eventually into 64 cubes. And what you see is that the surface area is growing very rapidly. When we have a lot more surface area exposed as we start to break this rock apart than we did before we broke it apart. And because rocks are relatively solid, not a lot of water or air is penetrating inside the rock. So almost all of the weathering is occurring at the surface. And if you increase the surface area, what you do is you increase the rate of weathering. And if you increase the rate of weathering, you increase the surface area. So this is a positive feedback loop. And this is why Earth is very efficient at recycling its surface. We don't have a lot of ancient rocks. In fact, our rock record stops right around 4 billion years ago. We really don't have many rocks from the first 500 million years of Earth's history, and that is because this process of weathering is so efficient. we don't really have a lot of impact craters preserved on Earth. If we look at the moon, it's essentially all impact craters because it doesn't have an atmosphere or a water cycle that's helping to drive these weathering processes. But on Earth, we have very few impact craters. We know that Earth must have been pummeled just like the moon, in fact, significantly more because the gravitational cross-section of Earth is much bigger than the moon. So anything that hits the moon was really coming in to whack into the Earth. The moon just got in the way. And so we know the Earth's surface has been pummeled by a host of meteorites, but we don't see a lot of those craters because of these processes, these really efficient weathering processes. Weathering is slightly different than erosion. Weathering is the breaking down of the rocks, and erosion is the separation and removal of those pieces of rock. Erosion is really the combination of processes like wind and water and glaciers and gravity that are taking these little bits of rocks and starting to take them away. Erosion is the small-scale transportation that we're going to eventually need to move these rocks away into places that we can eventually deposit them, bury them, and lithify them into a sedimentary rock. Transportation is the movement of these clasts once they've been weathered and eroded. That's going to be our short transportation. And eventually they're going to end up into one of three essential modes of transportation of sediment. That's either by wind in arid environments like deserts, ice, for example, like glaciers in mountain regions or near the poles, and primarily water in areas that have sufficient amount of water. You can see, for example, in both the center image and the image on the right, the glacier has a lot of darkness to it. There's a lot of grays and blacks in there. That's the sediment that's being carried by the ice. And you can see in the image of the river, this is from Brazil and the rainforest, all the brown in the water, that is all sediment that is being carried by the water. So we have to weather these things, erode them just by moving them towards one of these major modes of transportation, and eventually we're going to transport these things into a place where we can deposit them. Because deposition is the third necessary element before we make a sedimentary rock. Deposition is the process by which sediment settles out of whatever transportation medium is carrying it. The image on the left is the Mississippi River Delta. The Mississippi River Delta is actually two deltas now. You can see two real kind of dark brown areas. That's now where the Mississippi River is entering the Gulf of Mexico. As the Mississippi River is confined in the channel, as it's on land, the flows are relatively high. If you ever get a chance, you can watch along the Mississippi River barges that are going upstream compared to barges that are going downstream, and you can really see the velocity difference between those, and that tells you something about how fast the water is actually moving within the channel of the Mississippi River. When that water reaches the Gulf of Mexico, it's essentially reaching a body of water that's essentially stagnant. There's currents in the Gulf of Mexico, there's wave action, but comparatively to how fast the water is moving when it's confined in the channel of the Mississippi River, you can assume that the Gulf of Mexico is essentially stagnant. And as that water reaches the Gulf of Mexico, it loses energy because it's no longer confined in the channel. And what you see is that it starts to drop its sediment. You can see dark kind of brown clouds near the land edge. Those browns become lighter browns as you go away. Eventually, there's just these gentle wisps of a little bit of sediment as we go out farther from the river delta, the mouth of the river. And then as you get into the lower bit of that image on the left, you can see the deep blue crystal clear waters of the Gulf of Mexico, where now all the sediment has already been deposited and sank due to gravity, and we don't have any more sediment being carried out that distance. And so we need to deposit this material if we're eventually going to bury it and compact it and lithify it in our last step of making a sedimentary rock. That's because we need to squeeze out the pore space. So usually when sediment is deposited, it's deposited very loosely. And it's difficult to lithify a sedimentary rock on the image on the left there, where their grains are barely touching each other. There's a lot of open pore space. So the best way to get rid of that is to increase pressure. And so as we increase pressure by burial and by compaction, what we end up doing is we squeeze that pore space away. We start to get the grains are touching more. There's less of that pore space. And eventually we can start to precipitate some glue or some cement in the pore space, and we turned our sediments into sedimentary rock. We classify sedimentary rocks through a variety of characteristics: clast size, clast composition, the angularity and sphericity, how well they are sorted, and the character of the cement. Let's define each of those with an image and a quick slide. The clast size tells us something about the size of the bits and particles that are being made, were from the pre-existing rocks that are making the new sedimentary rock. When we hear terms like boulder and pebble and sand and silt, we don't really think of it, but it really does denote a size. So each of those terms doesn't tell you anything about the composition. You can have sand grains of any sort of composition, but it does tell you something about the size of that material. And so usually we like to define things by size. If it has cobbles and pebbles and things like that, we would call that a conglomerate, like you see on the left. If, for example, it's made of particles that are about sand-sized, we would call that a sandstone, that you see on the right. So the size of the fragments is important in terms of classifying the rock. The composition of the fragments is also important. Remember, we looked at a biochemical sedimentary rock earlier that we called coquina because the fragments were composed of shells, of little bits of biochemical fragments that were made from organisms. In this example here, this is a conglomerate. This is bits and pieces of other types of rock. So the composition of whatever the fragments are that are making our new sedimentary rock are also important in terms of our classification and naming. The angularity and the sphericity is also important. We like to look at how angular the little fragments are. This tells us something about how far the material has been transported. Remember, I mentioned earlier that we used the principle of uniformitarianism to look at certain geologic formations on the surface of Mars that suggest to us that there was liquid water on the surface of Mars. Much of that comes from this process of angularity and sphericity. The conglomerate, the rocks that we find on Mars, appear to have rounded edges. Those rounded edges are likely the result of a pebble rolling down a stream in the presence of water. And as it does that, it fractures its sharp edges and it grinds down into a more spherical shape. And so how angular or how spherical the grains are tells us something about how far the material has been transported. If it's highly angular, it's likely close to its source where it was formed, and thus it implies little transportation. If it's relatively round, then it's likely farther from the source that it was formed, and that implies significant transportation. Also, how well the material is sorted is very important. This also suggests something about how far things are transported. So because water, how big of a particle water can pick up is directly related to how much energy is in the system. As water starts to lose energy, it drops big things first, then it drops the medium things, then it drops the little things. And so it essentially will sort through the material that it's carrying. And again, if something is well sorted, that you see on the right, so the grains are all pretty equal in size. Usually they'll also be rounded, like you can see on the right. That implies significant transportation from where the sediment was originally formed. If things are poorly sorted, like you can see on the left, where we have big things and intermediate things and little things and everything in between, and the grains tend to have a little bit more angularity to them, that implies that we are close to the source and there has been little transportation. And finally, the character of the cement. What type of material is holding the clast together also dictates how we classify the rock. Usually the types of glues are calcite or quartz. And sedimentary rocks are very useful in our understanding of past environments. There's really no other type of rock that can tell us about, for example, past beaches or sand dunes, or where we had marshes and grasslands. The environmental clues that give us this information are destroyed in igneous and sedimentary rocks, but they're preserved in sedimentary rocks. So for understanding past environments, sedimentary rocks are really vital to that understanding. Let's talk about a few classes of sedimentary rocks. We've already introduced these. We focused a lot on clastic, but I just wanted to give you an example of biochemical, organic, and chemical sedimentary rocks. So here are some types of biochemical sedimentary rocks. These are primarily made out of limestone. That's a rock that is made of calcium carbonate, CaCO3. This is essentially the bones and, well, not bones, the shells and exoskeletons of little buggers that are living in marine environments. They're usually soft-bodied organisms, and in order to protect themselves from predation, they have exoskeletons, right? The shell of a mollusk, for example, or on the right, these are little tiny diatoms. These are little tiny plankton that create a little bit of a shell to keep themselves protected. So limestone is a great example of, for example, biochemical sedimentary rocks. Chert is another example of biochemical sedimentary rocks, very similar to the limestone, except this time the little buggers aren't making their shells out of limestone or calcium carbonate. They're making their shells out of silica, or essentially quartz. So these are little plankton that secrete silica, and that's what makes their exoskeletons. You can see they come in all cool shapes and sizes on the left there. Chert's also something that Native Americans used very commonly for arrowheads, for example, because you can get a very sharp surface from chert. And so this was a common tool-making rock type that was used by Native Americans. The example of organic sedimentary rock that we already discussed is coal. And so we're going to come back to this again, so we won't spend much time on this, but this is our best example of an organic sedimentary rock. And chemical sedimentary rocks are essentially those that form from the evaporation of water. If you've ever gone out into the southwest of the United States, you may have driven across some dry lake beds. These are known as playas, and they may have this white hue to them, and that white hue is essentially the sedimentary rocks that precipitated from solution the last time the lake had water in it. A lot of those lakes dried up during the last glacial maximum. As the glaciers melted, these lakes filled up, but they have no natural inputs right now, and they eventually evaporated as the climate became warmer from the time of the last ice age, but they left behind all of that material that was dissolved within them. And so you see these white hues sometimes that are the salts that are precipitated out of solution. So that's our most common type of chemical sedimentary rocks, which we call evaporites. Sedimentary rocks are very important about past environments, but not only because of the rocks themselves. So I mentioned that this tells us where we had, for example, coastlines where we find ripple marks or beaches, but we can also find in sedimentary rocks a lot of information within sedimentary structures. For example, sedimentary rocks are some of the only rocks, that preserve things like dinosaur footprints. And these tell us a lot about how dinosaurs could move, about their hip structure, about whether or not they stayed with their young, because we'll see bigger footprints with baby footprints next to them. So we gain a lot of information from the fossils themselves, but we don't really know much about how they moved and things like that. And so preserving things like footprints gives us a lot more information than we could just glean from the fossils themselves. Sedimentary structures are essentially defined or characterized by a few things. They're characterized by the layering of the sedimentary rocks. They're characterized by the surface features on those layers, for example, the footprint we just saw. And they're also characterized by the arrangement of grains within the layers. And all of these structures, it doesn't matter what the composition of the material is, it's these structures that tell us something about how these rocks were forming. When we talk about sedimentary structures, we use a few terms that you may not be familiar with. We use the term bed to define a single layer of sediment. We use the term bedding plane to denote the boundary between two of those layers or beds. Altogether, we call several beds strata, and the arrangement of the sediment is defined as bedding or stratification. Let me show you that in a picture that I think will make it a little bit more clear. This is an image of the Navajo sandstone from Zion National Park. This is evidence of a past desert environment that existed near the coastlines of the interior seaway that we know existed because of things like the ripple marks that I showed you from Colorado. And you can see these individual beds of this very sloping sediment, and then there's bedding planes that clearly denote one bed from the next. And then all together, this group that has these distinct angular beds, we would call a strata. And this is a past environment that's indicative of sand dunes. And so as this material is being laid down, we can go to a cliff face like you see in the upper right, and we can say something about the past environment. This is a road cut in Utah, about how the past environment changed. So we can see that there was some silt being laid down, probably due to river flow. We find bigger gravels that would be indicative of past flooding events, and then we start to see the silt coming back. So that means that the water now is flowing at a lower energy state because it can't pick up those bigger chunks of gravel, for example. It's just picking up the very fine silt. And so we can go to these stacked layers of rock and we can start to reconstruct what the environment of this area looked like over the last thousands, hundreds of thousands, millions, even billions of years. Here's that example of ripple marks. So ripple marks are a sedimentary structure. They are a surface structure. They're formed, for example, in beaches. You can see the left there, that's Cape Cod, Massachusetts. That wave action as the waves wash up and wash back as the tides change create these really distinct ripple marks. And there on the right is an image of a 145 million year old sandstone in the Dinosaur Ridge, Colorado area, where we also see these distinct ripple marks. And so as we talked about earlier, we can use the principle of uniformitarianism to suggest that 145 million years ago, near Dinosaur Ridge, Colorado, there was a beach environment that likely looked analogous to what Cape Cod, Massachusetts looks like today. The Navajo sandstone that we looked at in Zion National Park has those distinct, what we call cross beds. Those are those angular features of the beds. That's clearly denoting a dune environment. And we can go to modern sand dunes today, for example, Sand Dune National Park in Colorado. We can look at what the sediment looks like, and then we can compare that to Zion National Park, which is an amazing place if you ever get a chance to go. 200 to 180 million year old sandstone. We see those same types of features, and that structural evidence suggests to us that in this, where Zion exists today, 200 to or 180 million years ago, there were large sand dunes that existed there. Mud cracks are another surface sedimentary structure that we can see. So if you've ever been in an area that has significant rain but then dries up, so here in Alabama we'll have, especially in the springtime, we'll have pretty big rain events that could be followed by a really hot day where there's a lot of evaporation. And we'll see that where there's mud areas, that mud starts to evaporate. As the mud evaporates, it contracts a little bit because the water is leaving the structure of the sediment. And as the water leaves, everything contracts a little bit. And you get these really distinct cracks, which we call mud cracks. And we can actually find those preserved in sedimentary rocks. And that suggests to us that this was an area that would experience long periods of evaporation such that we could form these mud cracks. But one of the most unique things in sedimentary rocks is evidence of what we call trace fossils. So there's no actual bit of the living organism there, but there's a trace or a remnant of how that animal used to move or burrow or anything like that. And so you can imagine walking down a beach and then this beach being buried and compacted and lithified. Your footprints would essentially be trace fossils. We wouldn't actually have any bits of the living organism, but it's telling us something about the motion of a human body. One of the ways that we believe that humans are on the order of about 1.5 to 2 billion years old, even though we don't have a fossil record that goes back that far, is we have trace fossils of what appear to be hominids. They're bipedal, they stand up straight, they have a foot structure that looks different than, for example, our primate ancestors. And so it's these trace fossils, for example, in places like Kenya, Ethiopia, Eritrea, that tell us that it's likely that humans evolved somewhere in that area on the order of a couple to a few million years ago. This is Dinosaur Ridge in Morrison, Colorado, a wonderful place to visit if you ever have a chance. It is chock full of dinosaur footprints, tells us a lot of information about how big the stride was. That tells us something about how fast we think these animals could move above the land. Tells us a lot about their hip structures because we can see how far apart their strides are. And so we get a lot of information about motion of the animals that we don't really get from just the solid skeletal structure itself. And eventually the goal is to create what we call stratigraphic formations. And these are recognizable layers of specific sedimentary rocks that are deposited at certain time intervals and can be traced over broad regions. So the Grand Canyon is a nice big stratigraphic formation that tells us a lot about the history of the Southwest United States over hundreds of millions of years. And it tells us about certain depositional environments. And so we always want to be thinking about where is material being deposited. Sometimes material is deposited in a terrestrial environment, and that requires certain unique depositional environments. Sometimes, or usually, it's deposited in a marine environment. And then there is this transitional environment in between where the land meets the oceans. And each of these environments have different energies, and it's really back to the amount of energy in the system that dictates how much material it can be carried by the system. For example, a glacier is a depositional environment. So you can see here, this is a mountain glacier. You can see those dark stripes running down the middle. Those dark stripes running down the middle are where multiple glaciers started to meet together. So what that tells you is up above here, there was 3 glaciers where the 2 meet on the right. They are grinding material off on their edges, and then that material gets combined into that center dark stripe that we see on the right. We call that a moraine. And then there's 2 on the left that are, one on the left that's also meeting the center one, which makes another moraine. That's material that is being carried by the glacier. Glaciers are sometimes hundreds of meters, if not a couple kilometers thick. There's no problem for them to carry every size of material. You could drive a car onto there, and that car would happily be carried down slope as the glacier moves down slope due to gravity. So glaciers, although they're moving slow, they have an incredible amount of power. They can pick up and move essentially any size object that they want. Rivers are a little bit lower in terms of their energy, but they can still pick up a lot of coarse material. Here's a couple examples of some mountain streams, and you can see that there's some really pretty big boulders in there. So during heavy rain events, when these mountain streams start to flood, the energy of the water is sufficient to move pretty large bits of material. But usually when the flows are lower, it's really the small stuff that's being carried. That's why most streams, especially in the mountains, have all these large cobbles in them. The little stuff is efficiently carried away, but it's only during big rain events that these bigger material moves down slope. River environments carry a lot of sand and gravel. This is an ancient river bed that we can see in the upper rocks there. You see that kind of U-shaped channel that was carrying a lot of sediment. So usually once these rivers are getting out of their mountain environments, meaning the slope is decreasing, so as you leave the mountains and you come down into the low-lying areas, the slope of the river will slow down, the slope will decrease, so the velocity of the water will decrease. So usually now you're not carrying that big material anymore, you're carrying more fine material. There's also wind action that moves material, so sand dunes are evidence of wind erosion and wind transportation. One of the ways that we actually identified that Mars had a small atmosphere was that we started to notice that there were sand dunes on the surface of Mars, and those sand dunes were moving over time. And so usually in places that don't get a lot of precipitation, for example, desert environments, wind is the primary mode of transportation, and so wind is also moving and depositing material. For terrestrial environments that have a lot of deposition, we're usually going to be in places like lakes. So where rivers will reach a lake, whether it's a natural lake or a man-made reservoir, then the water will be stagnant in the lake, and as the river meets the lake, it will start to deposit and drop its material, and it will sort that material. Eventually, the terrestrial environment meets the marine environment, so this is what we call a transitional environment. This is where we have a lot of energy. Wave action is constantly working on the system. We have a lot of back and forth motion, so we get a lot of ripple marks that are formed. Usually we have things that are relatively well sorted and of relatively rounded sandstones. More transitional environments in terms of where the terrestrial environment meets the marine environment is, for example, a delta. So we talked a little bit about deltas already, where a river is confined into a channel but then meets a stagnant body of water. That river will start to drop its sediment, and as it drops its sediment, it creates this deltaic deposit where that material is now dropped, and as you move away into the water, you'll see that you drop finer and finer material. The bigger things come out first, and then the fines come out as you move away from the delta. As we get into marine environments, the marine environments are going to be dictated by how deep the water is. If it's shallow marine, usually it's close to a landmass. That means you're getting a lot of material from the river inputs, so we call that clastic deposits. You're going to get sands and silts and muds. But as you start to work your way away from the shallow marine environment into the deeper environment, that changes. In the deeper marine environment, you really have no input anymore from the landmass itself, and what you're dictated by is the skeletal remains of planktonic organisms that make things like chalk and chert. So there's no more inputs of the material that's coming in from the rivers, except maybe some really fine silts and clays, but it's really dominated by the skeletons of planktonic organisms that are within that area. And one thing that sedimentary rocks tell us a lot about also is they tell us a lot about sea level rise. And so sedimentary rocks is really how we monitor past and present, or past sea level. And so when we go through what we call a transgression, that's when sea level rises. What happens is the shoreline migrates inland. And so what we see is ripple marks and beach deposits that are moving inland towards the landmass. As we go through what we call regression, where sea level falls, we see that the shoreline migrates back outwards away from the landmass. And so we see our beach deposits and our ripple marks in areas that are moving towards the oceans and away from land. And so it's really the sedimentary rocks that tell us how sea level has changed in the past, which we'll come back to when we talk a little bit more about climate. All right, well, that's it. Thanks for tuning in to another lecture in the Introduction to Earth Science lecture series. We'll talk about metamorphic rocks next. Please follow me at Matthew Wielicki on Twitter and subscribe to this YouTube channel, and check out my Substack at noclimateemergency.substack.com. Thanks again and have a great day.